Hello, welcome friends. We shall continue our discussion. First, we will take up three phase induction motor drive control with CSI. Here, the induction motor is fed with CSI. What is that CSI? Current source inverter. For this, three phase bridge inverter is employed. And the current source we need to derive now, because normally we have voltage source. Current source needs to be derived. How do we derive a current source? We derive a current source by connecting a series inductor along with the normal voltage source. This is very important. Please try to recollect the definitions of current source and then voltage source. A voltage source is the one wherein the internal resistance or the impedance is, yeah, is very less, whereas current source is the one which has the internal resistance or the impedance very high, tending to infinity. These are the two definitions. And because of this, the terminal voltage, if this is the terminal voltage, the terminal voltage remains almost constant. And because of this particular feature, if the current is I here, the current I remains almost constant, independent of what we load we connect here. So even when we change the load here, the terminal voltage remains constant, because internal resistance or the impedance is almost zero. Whereas here, since the internal impedance or the resistance is very high, the current remains constant. The current remains constant, independent of the type of the load. Voltage source, voltage remaining constant. Current source, current remaining constant. So, in the case of current source, interestingly, even when we change the load to any extent, the current remains constant. Extend that logic a little. If I short this, then also the current remains constant. What does that mean? Looks interesting now. That means the current source configurations do not have the problem of short circuit as such. Do not have the problem of short circuit as such. Good. So, keeping that in mind, we will continue our discussion of this. So here the current source is derived by connecting a series inductor. It could have been a resistor also, but resistor results in a lot of loss, I square R loss. Hence, normally we go for an inductor in series with the voltage source. And when we have the three-phase bridge, the as mentioned here, that inverter, the current source inverter, that is three-phase bridge inverter, it employs capacitors for commutation of SCRs when the SCRs are used as control switches in the bridge. By controlling the current, the induction motor performance can be controlled. So look at the schematic now. Have a look at the schematic. We have three-phase induction motor, and then we have the bridge. This is the three-phase bridge, inverter bridge, supplied from current source, hence CS inverter, three-phase current source inverter. And here we have the voltage source, in series a very high inductor. Voltage source, high inductor in series together will make this a current source. So this current source, this is the current source. With this current source input, to this bridge, the bridge will become, this is an inverter bridge, hence it will become current source inverter. The output of this bridge, which is the AC, but the current output is the current here, that is fed to three-phase induction motor. Now the current source, voltage source in series with a very high inductance, the three-phase bridge, and then the three-phase induction motor, DC converted to AC inversion. For this we use a three-phase bridge. The three-phase bridge consists of 1, 2, 3, 4, 5, 6 SCRs. The bridge can as well consist of transistors. Here SCRs are used, and in addition to the SCRs, there are three capacitors. Can you see the three capacitors here? Yes, this, and then 6 diodes, D1, D2, D3, D4, D5, D6. D1, D2, D3, D4, D5, D6. So the bridge, have a look again. 6 SCRs, 6 diodes, and 6 capacitors. That's how the bridge configuration is. And the SCRs here are triggered using a controller. We have a controller which produces the triggering pulses or the firing pulses. Those firing pulses are fed to the SCRs, and the capacitors here along with the diodes will help to commutate the SCRs. The commutation, I will not go into the details of that. You try to recollect the current source inverter, typically the single phase version that we discussed when we discussed the power electronics. The commutation, how it happens, the triggering of the SCR in the Q next SCR will result in the commutation of the earlier SCR, something similar to complementary commutation, and that happens because of the capacitors here, and capacitors get charged to the required polarity for the commutation due to the presence of the diodes here. Okay, good. So the CSI is it converts the input, which is constant current. This is the input, the value is ID, continuous, that is converted into this output which we can control. The effective value of this we can control. Are you able to appreciate that? By controlling the firing pulses to the SCRs. Controlling the firing pulses to SCRs. Okay. So now this is fed to the three-phase induction motor, and when the three-phase induction motor is fed with this current, the value of which, effective value of which is changing, the induction motor performance will change. Depending on our expectation, we can manipulate the firing pulses, accordingly get the expected performance. Good. So the CSI fed three-phase induction motor, the drive control with this, it has the advantage that short circuit is not any issue here, understandably, because even if we short, the current will remain almost the same, no, not much of change, and that makes the protection of motor relatively simple. We need not worry about the short circuit condition as such. And commutation of SCRs is relatively simple. In the circuits involving SCRs, commutation is a problem. Commutation is to be done with a lot of care and poses a challenge. And in the case of the CS current source inverter, commutation is relatively simple with the configuration that is shown there, because we use capacitors. It's very simple commutation. Okay, it's, as I told earlier, it's almost like complementary commutation, triggering the SCR in the sequence next will automatically commutate the present SCR. Okay, and the CSI input to the motor, CSI fed induction motor, the control is better. Why that control is better? Because it is the current that is being controlled, and current is controlled directly, and that makes the control of the induction motor better, because it is the current which affects the torque and we are catching that current directly. Okay, it is not like you change the voltage and then the current changes, then the torque changes. It is not that way. So relatively the control of the induction motor is better. Whereas demerits, the very current source itself is a problem, because it is not a readily available source. It is to be realized with the available voltage source, and that requires large inductance to be connected in series. These are the demerits. Okay, next we will take up the three-phase induction motor operation. Three-phase induction motor operation with uh, unbalanced voltage supply. Induction motor three phase is fed with three phase supply, we know about that. And three phase supply is to be a balanced supply, we know that. Only when the supply is balanced in nature, the performance of the motor will be as per the specifications, because the motors are designed for balanced three phase supply. But there is no guarantee that the supply is always balanced. Quite possible that it is unbalanced at times. So what will be the effect of this unbalance of the voltage supply on the induction motor performance? How we can do that analysis? That's what we will see here. So when the three-phase AC supply, to the three-phase induction motor is balanced, the motor will perform properly, no doubt about it. If the voltages are unbalanced, then the performance will get deteriorated. It will become poor. The performance will become poor. And how do we analyze this? The analysis of motor performance with unbalanced voltage input can be done. Can you remember how? Employing symmetrical component theory. You have already come across this now. Symmetrical component theory. We use that symmetrical component theory. Employing that, we do the analysis. Now, what is the symmetrical component theory? As per this theory, the three-phase unbalanced supply, whatever voltages are there, they are represented in terms of three-phase balanced set of voltages, three groups: positive sequence, negative sequence, and then zero sequence. I repeat, the input voltages are now unbalanced. That is the reality. For our analysis purpose, what we do is, these unbalanced voltages we convert into three group of balanced voltages. What are those three groups? Number one, positive sequence group. Number two, negative sequence group. Number three, zero sequence group. And what are the equations employed for that? If the input set of voltages, the really available voltages are VA, VB, and VC, then they are converted into the three groups positive sequence Vp, negative sequence Vn, zero sequence V0 using the equations Vp equal to 1/3 Va plus alpha Vb plus alpha square Vc, Vn equal to 1/3 Va plus alpha square Vb plus alpha Vc, V0 equal to 1/3 Va plus Vb plus Vc, where this alpha is an operator e to the power j 120 degree or cos 120 plus j sin 120. Using these equations, we will get three set of voltages balanced, and those three sets of voltages are used for analysis purpose, because the analysis can be done with balanced voltages. So now we have got three groups: positive, negative, and then zero sequence. And to make our analysis simple, in the case of three-phase induction motor with star connection without neutral, zero sequence line voltage will be 0, and hence normally only Vp and Vn are taken into account. The positive sequence and the negative sequence are taken into account. And for each input voltage, positive sequence voltage or negative sequence voltage, the corresponding equivalent circuit parameters are used, and the analysis is carried out in the normal way. We know the analysis of the induction motor. We consider the input voltage, we use an equivalent circuit, then we try to find the current, voltage, torque, etc. The set approach is the only thing is that equivalent circuit we should take correctly, take properly. Here we are considering only a positive sequence and negative sequence. First we will consider the positive sequence. Look at this, the positive sequence. I am doing the analysis with positive sequence voltage, and when it is a positive sequence voltage, the slip is positive. If the slip for positive sequence is Sp, then it is equal to S itself. The positive sequence slip is the same as actual slip. Sp is equal to S. And the equivalent circuit consists of stator resistance, stator reactance, rotor reactance, and rotor resistance. Very normal parameters. And the supply voltage, its positive sequence voltage, per phase voltage we consider as Vp. Then the rotor current I dash Rp can be represented as voltage divided by impedance. This is the equation. Are you able to appreciate this? And when I know I dash Rp, the current, I can get the torque positive sequence, hence the subscript P is used, Tp equal to 3 times by omega ms I dash Rp square Rr dash by S. Are you able to appreciate this? Rotor loss per phase into 3 times divided by omega ms torque, and this gives us the torque corresponding to the positive sequence. We can get the omega t characteristics. We have the torque equation. This omega t characteristic is for positive sequence. Now we shall look at negative sequence. When the input is negative sequence voltage, the slip is negative because the voltages are having an opposite sequence. Slip is negative. If that slip corresponding to negative sequence we call as Sn, then Sn is equal to 2 minus S, where S is the normal slip. Now the equivalent circuit parameters, again Rs, Xs, Xr dash and Rr dash, but the slip is now Sn because it is negative sequence. And if the supply voltage, it is negative sequence voltage, the voltage per phase is Vn, then we will get the rotor current IRN dash I dash Rn as equal to voltage divided by impedance. Again watch the slip value Sn. Now with this we can find the torque Tn, the negative sequence torque, 3 by omega ms I dash Rn square Rr dash by Sn. So we can get the omega t characteristics with this torque equation is the, and this is the omega t characteristic for the negative sequence input. So that means we have the omega t characteristic for positive sequence as well as for negative sequence. Once we have that, if we plot it, then what do we find? This is what we are finding. The omega t characteristics for positive sequence will be this, for negative sequence it will be this, and the net performance of the motor is with positive as well as negative sequence both together. So the resultant performance or the net performance is actually the superposition of these two, that gives us the actual performance. This, are you able to see? The dotted ones are due to the unbalanced operation. This is the resultant. The unbalanced operation due to each group of voltage. We have made the analysis simple. The unbalanced voltage we decomposed into positive sequence and negative sequence. For each sequence we find the characteristic. The total characteristic is the sum of these two, the superposition. So net or effective characteristics of the induction motor will be simply the superposition of positive and the negative sequence. And you can observe here, if the unbalance were not to be there, then the negative sequence would have been absent. The whole voltage would have been positive sequence only. But due to the unbalance, the negative sequence comes into picture. As a result, the actual characteristic what we get will be this. What do you observe? The torque becomes less. Are you able to see here? The torque becomes less. That is the main effect of unbalanced operation. So we shall look at the effects of unbalanced voltage. The effects of unbalanced voltage. The very first thing is, due to negative sequence, the net torque is reduced. Just now we saw in the omega t characteristic. And then due to negative sequence voltage, the negative sequence current will flow in the winding, and that creates I square R loss. This adds to the total loss, thereby decreasing the efficiency, because the total I square R loss will become more, the efficiency will be less. And also the heating will be too much because the total I square R loss will be more. That is why normally they say when it is an unbalanced operation, motor gets overheated. The reason for this is that negative sequence group of voltage and the corresponding current, negative sequence current. Next, the unbalanced supply voltage generates pulsating torques, and because of this the performance becomes very poor. Particularly when the single phasing happens. Single phasing is the worst type of unbalance. What do you mean by single phasing? One phase itself not there, one phase voltage itself is zero. When this happens, this is the worst unbalance. When this happens, then if it is happening at the beginning only, if we try to start the motor will not start. If the motor is already running and single phasing happens now, then the three phase induction motor will continue to run, but as single phase motor. Listen to me carefully. If the single phasing has happened, three phase motor is there, we try to start, it doesn't start, because it doesn't have the starting torque as such. If the motor is already started, earlier the three-phase voltages were the motor is running, but now suddenly one phase misses, single phasing happens, and motor will not stop because it has already started running now. It will continue to run a single phase motor, but because of that there will be overheating of windings. Because of that there will be overheating of windings, and if the protection is not given, the motor itself might get totally damaged. So look at this effects of unbalanced voltages. Typically the single phasing there, that's why normally in the case of induction motors you will find single phasing protection normally provided. Good. Okay. So next we will continue our discussion. Look at this transient analysis. We'll have a small discussion about this. Transient analysis is actually analysis corresponding to the operations like starting, breaking, etc. Starting, breaking, which occur for a very short duration. We'll take one typical situation, the transient operation like starting, let us say, and transient analysis we do to find different things of our interest, like how much is the time taken, how much is the value of different parameters there, like the current there, the voltage there, the energy there, etc. So we'll take one example, the energy loss during starting. How we can do this, how we can find this? Consider an induction motor starting from rest. When I say it is starting from rest, what is the corresponding slip? S equal to 1, and it is starting, it reaches equilibrium, and that equilibrium state normally nearer to the synchronous speed, hence the corresponding slip we can take it as nearing to 0. So the process is starting, which is actually corresponding to s equal to 1 to s equal to 0, that interval. The energy loss during this period, that period if I call as ts, the starting time, we can obtain as ESR, the energy loss in the rotor during starting, I dash r square rr dash one winding rotor I square r loss, like that 3 windings total rotor loss, this is the power loss, into time energy over a period dt, that way from 0 to ts total energy loss. I repeat, I dash r rotor current, I dash r square rr dash rotor resistance I square r loss for one phase, for 3 phases 3 into this is the power loss, into time energy loss for a period dt, for the total starting duration, integrate this from 0 to ts, and this 3 I dash r square rr dash is actually s into pz, where s is the slip, pz is the gross power developed. This I can as well put as s into t into omega ms, where s is the slip and then t is the torque generated and omega ms is the synchronous speed. And for an induction motor we have the basic torque equation, simple, j d omega m by dt equal to t. You remember that basic torque equation? In a simplified version I can write it like this. This I can put as t dt equal to minus j omega ms ds. t dt equal to minus j omega ms ds by taking this differentiation. Now omega m is the actual speed is equal to 1 minus s omega ms. This ESR equation I can now put as starting s equal to 1 to almost s equal to 0, that is the starting activity, s into omega ms, t dt is minus j omega ms ds, and this if we integrate we will get 1 by 2 j omega ms square, 1 by 2 j omega ms square, that is the loss during starting, and it is half j omega square. What is that half j omega square? Half j omega square is actually the kinetic energy stored, kinetic energy stored. So the amount of loss during starting is actually equal to the amount of kinetic energy stored in the motor. Are you able to appreciate that? So this way, here we found during one transient activity, that is starting. This way we can find in different transient activities the energy loss, like during braking, and it can be different types of braking like plugging or rheostatic braking, etc. Even the deceleration and acceleration events also, we can do such analysis. This is how the transient analysis is attacked. Next, look at this, the single phase induction motor, how it is controlled. Single phase induction motor is controlled using a very simple approach. Can you see the schematic here? Voltage control is the principle employed. How do you control the voltage? Using two SCRs connected in anti-parallel. It could have been a single device like triac, but we know already that triac has some issues like unsymmetrical triggering. Hence, normally anti-parallel connected SCRs are used. So, the normal and simple approach to control the single phase induction motor is to have a voltage controller. It is actually voltage controller, and that is done with the help of anti-parallel connected SCRs as shown in this figure. By controlling the firing angle to these SCRs, the effective value of voltage supplied to the induction motor is changed, and thereby the speed is changed. So look at the schematic. We have single phase AC fixed, we have two SCRs connected anti-parallel, single phase induction motor, input voltage is Vin, output voltage is V0. By controlling alpha, the firing angle to the SCRs, so we have the controller, this is the controller which feeds firing angles, firing signals to the SCRs. The firing angle of these signals can be changed. When we change that alpha, the effective value of V0 will change, hence the speed of this motor will change. So the motor, what speed it runs, that value will change. This is how normally the single phase induction motor is controlled. Is it okay? So we shall stop there. With that, we are coming to the end of this unit, the induction motor drive. Okay, bye, take care.